Hello. I can start. My name is Cezar, and today I will talk about how to securely share references between verified and unverified code in F-star. So for the ones who don't know, F-star is a proof-oriented language in which one can verify programs. So usually one writes a program using a shallow embedding, writes a specification by annotating the code using refinement types and pre and post conditions. And then the F-star type checker checks if the code satisfies the specification, the annotations. And if the answer is yes, then we have a guarantee that the code satisfies the specification. And this was used, F-star was used to verify two big projects and many more, but I want to talk about these two. Evercrypt, which is a cryptographic provider that's verified in F-star, and code generated from F-star is now part of Mozilla Firefox, the Linux kernel, and the WireGuard VPN. And Everparse is a framework for secure parsers, and parsers verified using this framework are now part of Windows Hyper-V, and which is part of Azure Cloud. So these projects got integrated into larger code bases. However, mixing verified code with unverified code can be problematic. And this is because the interaction between verified code and unverified code is usually assumed, meaning that the behavior of the unverified code is assumed. So because there is no guarantee that these assumptions are satisfied, if the unverified code is buggy or malicious, this can lead to unsoundness and insecurity, which will break our verification. So the solution we propose is to enforce the assumption on the unverified code by using dynamic and static enforcement. And we want to do this in such a way that we have here, we are able to write a global specification about the whole program. So we want to state a specification that relates the initial state and the final state of this whole program. So in our setting, both the verified code and the unverified code are stateful programs. You can think of them as being written in the same language, but one is verified, the other is not. And they can dynamically allocate first-order ML mutable references. These are also known as full-ground references. And it means that they are typed references, they are unfreeable, and they are also unforgeable. And also in our setting, the two can share references dynamically between them. So in this setting, what we do is that we use dynamic enforcement to enforce the assumptions that the verified program makes about the unverified code related to the shared references. So you can imagine that the verified code can expect from the unverified code a reference that should contain a sorted list. This can be an assumption one writes. Obviously, there is no way to guarantee that the unverified code gives us that. So we enforce this using higher-order contracts. And what we enforce statically is that we prove that the unverified code modifies only shared references. So the intuition behind this is that we treat the dynamically allocated references of the unverified code as being shared. And also, we know that the unverified code cannot get their hands on the references of the verified code because they are unforgeable. So these two ingredients are enough to get back our specification, and we had to have a proof, a mechanized proof, that our whole program satisfies the specification. And to make it clear, this proof is done for any piece of unverified code. So given a verified program, and given that's verified with related to this global specification, this can be linked with any piece of unverified code, and it will still be secure. All right, so to obtain this result, to have this strong guarantee, one has to use SecRef star. It's a framework we introduced. It's a verified secure compilation framework for the sound verification of stateful partial programs. So one can verify a stateful program using SecRef star. During compilation, the higher order contracts will be introduced. And then The compiled program can be linked with any piece of unverified code. And SecRef star is shown to be sound and secure as long as the verified code and the unverified code are shallowly embedded in F star into a monad that supports terminating higher order stateful programs. Yeah, so this part of F star is secure. We obviously have extraction to a camel, but that's not verified, so it's not part of the dog. So I would like to give you a glimpse of three of the contributions of the paper. First, how to verify soundly partial programs. I will give you some intuition about why SecRef is sound and why it is secure. We prove about SecRef star that it preserves observational equivalence, non-interference, and trace properties. So here we have a program, and on the right we have a model of a heap. So this is a higher order program that takes an unverified library as an argument. So the unverified library is of type ref of int and returns a callback unit to unit. And the first thing the program does is that it allocates a reference where it keeps a secret. It will appear on the heap. It allocates R, which is a ref of int. And then it calls the unverified library, and it passes R to the unverified library. So what happens in this moment is that R gets shared, and also where R points to gets shared, which brings us to the property of sharing is that it's transitive and permanent. And now, because the unverified library has access to R, we don't know how the unverified library modified R. It could stay the same, it could not, we don't know. Next, the program allocates a new reference and updates R to point to this new reference. And then it calls the callback that it got from the unverified library. So here we call the callback with unit, but this callback still has access to R and R prime. And by rereading R and R prime, it will also find this new location, which means that this new location is also shared. And now we see that looking at what references get shared is not as easy as looking what references are passed. We passed directly only one reference, and that's R. But here, 3 references got shared. And because this makes tracking what's shared tricky, and when here to be able to verify this program on the next assertions, we have to be able to answer the question, what references can this callback modify? And so this is an assumption we make about the unverified program. And if we under-approximate, we risk to be unsound. If we over-approximate too much, we risk to not be able to prove this assertion. So to tame this complexity, we propose to over-approximate what references get shared using labels. So we introduce a labeling mechanism that's encoded in F star, so we don't change anything from how F star works. And this labeling mechanism is computationally irrelevant. This labeling mechanism doesn't exist at runtime. It's used only to do proofs. So fresh references are labeled as private, start as private. And then we have a dynamic operation that the user can use to label a reference as shareable. And there are 3 rules. Once a reference is labeled as shareable, it's forever shareable. Shareable references are only allowed to point to shareable references. And only shareable references can be passed between the verified and the unverified code. So having these rules is enough to verify our code. And let's look back at our example to see how that works. So now you see that in the heap, we have a ghost map that maps references to labels. But again, this is ghost. This doesn't exist at runtime. But during proofs, this map will get updated. So this is why it's kind of a dynamic operation. So the program allocates the secret, and it will be start as private. It allocates R, it starts as private. And then the user has to use this dynamic operation manually to label R as shareable. And the user cannot forget to do this, because part of SecRef, the assumption made about the unverified code get extended. Now we assume about the unverified library that it accepts and returns only shareable references. So when the user tries to call the unverified library, they actually have to prove that R is labeled as shareable. And because we are in F star, this is done using the SMT, which simplifies things. So again, we don't know how R and R prime get modified. And the user also has to, when updates the shareable references, again, the user has to use the dynamic operation. And this is because now the update states that, okay, if you want to update the shareable references, then you have to prove that the new value also is shareable. And now when we call the callback, we can do something very nice, is that we can use the labels to strengthen the post-condition of the unverified code. We can say that the unverified code modifies only shareable references. And and this is very helpful because next, when we try to prove our assertion, we see that secret is private. We know that the calls into the unverified code modified only shareable references, so we can prove that secret stays the same. So I showed you how one verifies a program. I would like to talk more about how the program assumes what the unverified code does. So the assumptions are all in the types. And we say that the verified code assumes a strong type of the unverified library. This is a type that contains refinements and pre and post conditions. So here we see that the unverified library is a function that takes a ref of int and returns a computation in LR. LR is our shallow embedding using a monad. And this monad is special because it has a precondition. So this precondition states is a predicate over the initial heap, and it has two parts. The first one is specific to SecRef star. It states that R has to be shareable, and the second one is user provided, and it states that R has to contain an even number. The monad also gives us a post condition, which is a predicate over the initial heap and the final heap. And the first two are specific to SecRef star. Between the initial heap and the final heap, only shareable references get modified, and the return value has to be shareable. In our case, it's a callback, so that's considered shareable because it's not stored in a reference. And also we see a last conjunct that states that R has to be unchanged. This is again something specific to the user. That user gives. So the user uses this strong type to verify the program, and then during compilation, this type will get simplified to something we call an intermediate type. So compilation, in our case, will convert the user-provided predicates into dynamic checks, or some of them will even be enforced statically. So here, in the precondition of the unverified code, we have this predicate that will be statically verified when verifying the code. So actually, this doesn't have to be enforced dynamically. But the second one is a post-conditional of the unverified code. There is no way to know statically that the unverified code doesn't change the where R, the value of R. So here, what we do is that we add a higher order contract that will save R before calling into the unverified code, and then do the dynamic check when unverified code gives us back on control. Yeah, this is a standard stateful contract. And finally, the intermediate type will look something like this, which now it contains only predicates specific to SecRef star, our framework. What about the unverified code? We say that the unverified code has a weak type, and we can bring this weak type to an intermediate type. So let me show you how we do this. So actually, we take advantage of polymorphism by parameterizing the type in the specific predicates of our framework. So first, we use some notation. We use phi to define is shareable, and then modifies only shareable. We denote with less than equal. And then we parameterize this type into these predicates. So now what happened is that this type doesn't have any concrete specifications, which we say that it's a correct representation or appropriate representation for unverified code. And what's nice about this representation is that if we instantiate back this type with our predicates, we get the proof that we want, that the type we had earlier that states that unverified code modifies only shareable references. So we get this basically for free when doing this. So the full details of this are in the paper. Here I can say that this type is also parametric into the operation of the monad. And those operations also use this phi and less than equal, like the parameters. And they compose really nicely, and this allows us to do this claim of that is unverified code. And also we have a translation from a deeply embedded language into this representation. So we really think that this is an appropriate representation. Okay, so we saw how to verify a partial program. I gave you some intuition about why it's secure, why it's sound, and I want to talk now about why it's secure. So it's we prove about our compiler that it satisfies robust relational hyperproperty preservation. This is a strong secure compilation criterion. It's the strongest of the work of Abate et al. And it's specifically stronger than full abstraction. So compilation, in our case, preserves observational equivalence. So this is what full abstraction gives us. But our criterion also gives us that it preserves non-interference, and it also preserves trace properties. And it's usually very hard to prove, but our proof is by construction. We use shallow embeddings for the source and target language, and we have a specialized design of the higher order contracts. So there is more in the paper that I do not have time to talk about. I didn't talk at all about the shallow embedding, which is the extra monad. And actually, we give a monadic representation for monotonic state, which is the main way to verify stateful programs in F-star. It was previously fully axiomatized in F-star. Now it's a lot less. And we give a proof of soundness. We show how we encode the labeling mechanism on top of this monotonic state, and we also have more labels for higher order settings. And also we have an interesting case study of a simple cooperative multi-threading scheduler. So the scheduler is verified, but it schedules unverified threads, and we still are able to prove that the scheduler is fair. Yeah, that was it. Thank you.
All right. Do we have any questions? Or, sorry, you're there first. Go ahead, Sean.
Hello. First of all, thank you for the talk. I thoroughly enjoyed it. I recall from some of the gradual typing literature that sound gradual typing can have some quite unfortunate performance trade-offs. I know that some work has been done around static analyses to try to lessen these issues. But given that F star is in a dependently typed setting, I'm curious whether or not you have an idea for how the more complex type systems interact with these dynamic contracts with regards to performance overhead and whether or not you've done any benchmarks on that.
So we did not do any benchmarks. We only enforce properties, predicates about shared references. So in a way, and we don't look at the unverified code at all, right? We don't apply any analysis to the unverified code. So basically, we don't have any way to know if this predicates hold or not, except doing a dynamic check. So these dynamic checks are unavoidable. Because they are only about the shared references. The other properties enforce statically, so we save a lot of time on that. And I think there is some related work that adds dynamic check also for that, like to make sure that the private references of the verified code stay the same. We don't have to do that, so that is an improvement on our side.
Okay. Makes sense. Thank you very much.
For your talk. I know that in Jane Street they tried modifying OCaml compiler to add some modes to it, and in particular they added local and global mode to variables. But in their application, it's for optimizing heap allocation. But they have very similar rules. They have like, if a variable is local, it became global, then it never becomes local again. I wonder whether you looked at this work and maybe they have similar implementation, or maybe they have similar properties, or maybe your is completely different. Yeah, what's the relation?
So our work is more coarse-grained. We split into verified and unverified code. Their work is more fine-grained, is at the level of each function, right? And also we are in the setting where we verify programs that are shallowly embedded in F star. And I read their paper, but I don't know a good way to shallowly embed the modes they are using into F star so that I can take advantage of them, so that I can verify the code and then extract, right? So if you have any ideas about how to shallowly embed modes in F star, how to shallowly embed modes, then I'll be happy to hear about it. And
okay, thanks. First, I need to understand what does it mean to shallowly embed modes.
This is kind of maybe a follow-up question about the overhead of the contracts. So I guess maybe one way to phrase it is when you're doing those higher order contracts, does that involve creating proxies on the references or no?
No.
Okay, cool. And then follow-up is, does it are those checks always sort of like O of 1, like time complexity, or could they involve like traversing a big chunk of the heap or something like that?
Right, so something I did not say is that the predicates are written, they are logical predicates, and we don't have a way to convert them to dynamic checks automatically. Mm-hmm. So the user has to provide these dynamic checks. Okay. And here it's the user who decides. I suppose it's a balance between having very complicated predicates that take a long time to enforce, or maybe relaxing a bit. Mm-hmm. But again, these are about shared references, so one doesn't have a choice but to dynamically check what happened there.
Okay, great, thank you. All right, let's thank our speaker again.